Hello everyone, welcome to Sam Science View channel. In today's video, we are going to see about science behind swimming, in specific freestyle. Before going into the video, please do like, share and subscribe to my channel and watch this entire video. Now let's get into the video. Swimming is a popular activity both for recreation and competition. The physics of swimming involves an interaction of forces between the water and the swimmer. It is these forces which propel a swimmer through the water. In order to swim, a swimmer must push against the water using a variety of techniques. There are four major techniques or styles used for swimming. They are front crawl, that is freestyle, breaststroke, backstroke and butterfly stroke. In competitive swimming, these are the four techniques used in the numerous swimming events. Out of these, front crawl, that is freestyle, is the fastest mode of swimming. We are going to discuss about this freestyle in detail. The key for every swimmer is to start with Newton's 3 laws of motion. The first law states that an object at rest will remain at rest unless acted upon by an unbalanced force. In relation to swimming, this means a resting body wants to stay at rest and it takes energy to get moving. It is manifest in the way that swimmers must jump or push off the side of the pool to get going. The second law states that force is equal to mass times acceleration, which means that if two swimmers of the same mass push off the wall at the same time but do not make any strokes, the one who used the most force will go the farthest. This person had greater acceleration and therefore exerted greater force. This explains why some swimmers are faster than others. And Newton's third law states that for every action there is an equal and opposite reaction. Thus, swimmers must stroke downward in the water to stay afloat and propel forward. This movement is equal and opposite to the force the water exerts against the swimmer to stop them from moving. Now, let's see forces acting on a floating body. In order to float in water, an object must be less dense than the water. This difference in density causes the object to float. This happens by way of a buoyancy force that lifts the object. The principle behind this lift is called Archimedes Principle, which states that any object, regardless of its shape, that is suspended in a fluid like water is acted upon by an upward Biond force equal to the weight of the fluid that is displaced by the object. When an object is placed in a fluid such as water and floats as a result, the part of the object that lies below the surface of the water displaces the water weight equal to the weight of the object. This weight is equal to the Biond force pushing upward on the object. The amount that the object sinks below the water surface corresponds to the equilibrium point in which the object weight is equal to the Biond force pushing upward on the object. Furthermore, the Biond force acts through the center of buoyancy, which is the centroid of the immersed part of the object, which is the volume of the water that is displaced by the object. For the object to maintain its orientation in the water, that is not rotate, this Biond force must pass through the center of mass of the object. If this Biond force does not pass through the center of mass and is offset from it, as we can see in this picture, then the object will rotate until the Biond force passes through the center of mass. At this point, rotational equilibrium is reached. As we can see in the picture, the Biond Force acts at the point that is to the right of the center of mass, and as a result will cause the swimmer to rotate counterclockwise. In addition to eventually reaching rotational equilibrium, an object floating in water will eventually also reach translational equilibrium. This is when the upward Biond force acting on the object is equal to the weight of the object. When both of these conditions are in equilibrium or reached, the object stays stationary. An object that is in equilibrium will always satisfy both translational and rotational equilibrium. Now let's see how these forces acting on swimmer makes them to move through the water. A swimmer propelling themselves through the water has four basic types of forces acting on them, which we can see in this picture. By moving their arms through the water, the swimmer creates a thrust force that propels the swimmer forward. For a swimmer moving at constant speed through the water, the thrust force is equal to the drag force. This drag force is created by the motion of the swimmer through the water. This force resists the motion of the swimmer through the water. A drag force exists any time an object moves through a fluid such as air or water. Here it is water. The faster an object moves through a fluid, the greater the drag force. The drag experienced by a swimmer swimming at the surface can be broken down into three components. First, it is pressure drag or a form drag, which is due to the swimmer pushing the water out of the way as he swims along. And the second, skin friction drag, which is due to the friction between the water and the swimmer's body as the water flows over it. This type of friction occurs inside the very thin layer of water directly touching the swimmer's body. And thirdly, wave drag, which is the drag due to surface waves produced by the swimmer as he swims along. Special body suits serve to reduce skin friction drag, allowing swimmers to swim faster. Now, for front crawl swimming, the thrust force is primarily created by the swimmer's arms, which consist of upper arm, forearm, and hand as they move through the water. The kicking action by the swimmer's feet also provides some thrust while also helping to keep the swimmer's body level streamlined with the water, which helps to reduce drag. The hands as a source of thrust are a very controllable part of a swimmer's technique and are therefore an important performance area to optimize for competitive swimming. The swimmer's hands mimic an airplane wing in the way they generate force as they move through the water. We can see this illustration in the picture. Just like for an airplane wing, the convention for showing the forces acting on the hand is to break them down into a drag force and a lift force. The drag force acts in the same direction as the oncoming flow velocity. The lift force acts perpendicular to the flow velocity and points in the direction of inclination of the hand relative to the flow velocity. The amount of inclination is given by the angle of attack. The magnitude of the lift force and drag force is related to the angle of attack. The resultant force is the vector sum of the lift force and drag force. This is the actual force that acts on the hand and is felt by the swimmer as it moves through the water at velocity v. Note that the swimmer can move his hands in any three-dimensional direction in the water causing the lift and drag forces and resultant force to act in any direction also. Swimmers use a complicated hand motion to generate the maximum thrust possible depending on the swimming style used. We can see this in the picture for the front crawl. Note that D is the drag force acting on the swimmer's hand, L is the lift force acting on the swimmer's hand, and R is the resultant force acting on the swimmer's hand. By moving his hand along an optimal path as shown here and adjusting the orientation of his hand through, that is the angle of attack, the swimmer can maximize the resultant force and keep it pointing forward as much as possible. The ability of a swimmer to do this comes down to his feel for the water, which is a function of swimming talent. The hand is represented schematically by a wing, which, as explained previously, experiences lift and drag forces, as we can see in this picture. When a competitive swimmer moves through the water, his intent is to maximize the thrust force generated which propels him along. In addition, the swimmer desires to minimize the drag force experienced by his body as it moves through the water. This is done by keeping his body as straight as possible along the direction of travel. This has the effect of minimizing his frontal area in the direction of motion, which minimizes pressure drag. This concept can be noticed in this picture. Note that the drag force that a swimmer wishes to minimize is the drag force resisting the movement of his body through the water. This is different from the drag force generated by the swimmer's arms and feet as he moves them through the water. In this case, the swimmer wants to maximize this drag force since this is what propels him forward. So these are the science facts which are found behind the swimming. So that's it for today's video. Hope you got some science related facts in this sports, especially freestyle swimming. Do like, share, comment about this video, and we'll see in the next science behind sports series. Until then, take care. Goodbye from Sam.